Now, these changes are because now what is going on now? Now the tangential stress sigma tau r, and these changes have become because the phase b dash or at the distance delta r away from phase a dash d dash. On phase d c dash d dash, what happens? Now d c d dash c dash d dash, which is next phase is b. B dash c dash b dash a dash d dash लगता है on the phase on phase these changes are because of the phase d c dash on this phase d c dash d dash. D c dash d dash is the phase itself. What is that? D c dash d dash itself. What is d? What is d c dash c dash. This is the phase itself. This is the particle phase d c dash d dash. The phase on it, what is going on is like this. Now this is sigma theta. It is because this is acting along the circumference, and theta is the measurement of the circumferential length, and the tangential stress is tau r theta and tau theta z. Tau r theta, tau theta z itself. What is tau r theta? It is acting both these things acting along the circumference z theta, and this is acting along the axis and longitudinal axis z itself. Here it is along the radius along the radius itself, and here it is along the circumference itself. So on the last phase a b dash a dash, that is, let us see what is this. It is just opposite to this phase. So this is angle is increased by delta sigma delta theta plus d tau theta d delta theta by d theta multiplied by delta theta, which means one phase stress is sigma theta. We are saying that according to the change in the dimension delta theta, the rate of change of this stress is d delta theta by d theta. This is multiplied by the change in length, that is delta theta. The tangential stress tau here follows the same principle. The original length, original value of the tau, multiply this rate of change of this tau with theta, multiplied by the change in length, that is theta, and rate of change of this tau with theta multiplied by the change in length, here is also theta itself. So the changes in the above components are because the phase a dash a b dash a b dash is separated by an angle delta theta from this angle d c dash d dash on the phase a dash b dash c dash d dash itself. Now on the phase a dash b dash c dash d dash, which is that which is this plane, that is normal phase a b dash c dash d dash. Take action. It is a b dash c dash d dash. A dash b dash c dash d dash means a dash b dash c dash d dash. This particular plane itself. Then The bottom plane. Here, the normal stress is sigma z, means what this bottom plane itself. Bottom plane itself, the normal stress will be along the longitudinal axis z, and tangential stress will be both are along the longitudinal axis, and one is normal to the y. One, it is not y itself. It is actually, this is r. It is r. It's rz, r theta j. Tau r. It is along the radius. Along the radius axis is along the theta itself. On the face ABCD, means just above the top face, we have tau r theta rz. We are following the same thing, rate of change of this shear stress and rate of change of this normal stress with respect to dz, rate of change of this length dz multiplied by change in length delta z. So we are having this thing. So what we have taken out a portion of from the surface of our prismatic bar cylindrical element, and we have a six-sided prism of six unequal sides, and first from top side facing the radius and to the side opposite to it, we are finding out the area, and then we have calculated what is the stress acting over these two faces, then bottom face and top face, then right side and back, front face and back face. We have find out the area, as well as then we find out what are the stress acting over it. Other than these forces, what we know is the gamma r, gamma theta, gamma zeta. Theta is the gamma z. It is the body force component per unit volume itself. If the element is equilibrium, now we have to say, we know the element is equilibrium, there is no unbalanced force. So the sum of forces along r, z, theta, and z direction must be equal to 0. So along r direction means radial direction. We have calculated the longitudinal stress along the r direction multiplied by the area itself, and shear stress along z direction multiplied by the area itself, and this is away from the radius. This is the going towards radius, the negative. That's why it is negative. Sigma r radius into r theta theta z 8 r plus delta r plus theta sine theta sine. It is the angle of delta theta divided by 2 multiplied by delta theta. Thus, we have adding and subtracting all these angles and equating them to 0. We will get this equation like this here. Next. Equation 5. Cancelling terms and dividing it by delta theta, delta r, delta z, cancelling all the small terms and going to the limit with delta theta, delta r, and delta z all tending to 0. So we have got this, that situation is reduced to r delta theta divided by delta r del tau xr by dz, tau r theta by r theta, tau r minus tau theta plus tau r gamma is equal to 0. Or sigma, this equation is reduces to, if we divide by r, this is 1 by r, this r is reduced, 1 by r is here, this is by r, this is also r by gamma into r itself. Similarly, we consider the equilibrium in m and theta direction. This is not m but in a z and theta direction, we get the similar equation like this. This 1, 2, and 3 is defined as the differential equation of equilibrium expressed in polar coordinates itself. Now, this axisymmetric case and plane stress case, axisymmetric case and axisymmetric case and plane stress case. Let us consider another case like this. If an axisymmetric body is loaded symmetrically, the stress component do not depend on theta itself, which is saying like this. If an axisymmetric body loaded symmetrically means both sides are equal. It is along, there is an axis and it's a round shape along the axis, and both sides are equally loaded equally or loaded symmetrically. The stress components do not depend on theta itself. So deformation is symmetric. So tau r into theta, tau theta into z does not exist at all. So there is no shear stress along over the surface along the theta, along the length theta, and normal to the plane r, and there is no shear stress or normal to the plane theta along coming from the z itself. So those components of shear stress does not exist, and consequently the above says this is equally loaded. So there is no stress happening over the surface like this. Those shear stress happening over the surface. Thus, the above set of equation, in the absence of body forces, if there is no body forces like gamma theta, etc., this equation, these three equations are reduces to like delta sigma z by delta, delta tau r by delta z, delta r minus delta theta by r, and same. And the third axis, it does not exist because all of them are equal to 0. Then the equation reduces to two equations like this here. Now, a sphere under dimensional compression, diametrical compression, or a cone under a load at the apex are examples of which above set of equations are applied. Diametrical compression means all the loads are acting towards the diameter, along the diameter, no force is acting along the circumference itself. So all the shear stress of the circumferences are reduces to 0. If the state of stress in two-dimensional in nature, that is plane stress, plane state of stress, the only sigma theta, tau r theta, gamma vector exists. In two-dimensional, if stress is two-dimensional nature, only plane stress. Only the stress along the radius, stress along the circumferences, normal stress along the circumferences, and tau r theta means the stress along the length theta, and normal to the which is normal to the radius r, and on the angle on the radius angle r, I mean radial plane r, and gamma r and gamma theta, the body force along the radius and body force along the theta exists. The other components vanish. This non-vanishing state component depends only on theta and r and independent of z itself in the absence of body forces itself. So these parallel equations of equilibrium again reduces to dr theta by dr 1 by r d tau r by d theta plus sigma r minus sigma theta divided by r equal to 0. D tau r theta by dr 1 by r d theta by theta is 2 tau r by theta is equal to 0. So thus we have got a differential state of equation, and we have got a differential state of equation first like this. We have 1, 2, and 3 set of equation. Next, we are assuming different axisymmetric case. First, what we have divided the load. First, load is symmetrical. Means load is don't have an equal. Symmetrical means what we mean. This body is totally symmetrical means it is equally spaced in along its say longitudinal axis itself, and it is loaded symmetrically. Means if it is loaded only on the surface itself, not along the length, so the stresses component does not depend on theta. Means what is theta? It is the on any point on the surface, the radial polar coordinates